My name is Evangelista, and welcome to another episode of Evangelista Science of the IB Chem SL Curriculum. We're going to do 2-2, which is Electron Configuration. First thing we're going to talk about is this is the electromagnetic spectrum. We have different radiations here, and the shorter the wavelength, the larger the energy is what you need to know from this. The longer the wavelengths, or the distance between the crests or the troughs of these waves, the less the energy. So we're going to focus mostly on visible light, which is right here. And just note that the purple light is more in energy than the red light because the wavelengths are going to be longer. Here's a continuous spectrum, and we're going to find out why this is more important later. Okay, so let's talk about the Bohr model. So the Bohr model has the nucleus in the middle and the electrons in these very specific rings or orbitals outside of the nucleus. What you need to know is that an electron can be excited past its ground state, either by shooting it with photons or energizing it. But it can be energized, and when it gets energized, it goes up these energy levels, and eventually it's going to release that energy that it absorbed and jump back down to the ground state. Now, when it jumps down these energy levels, it releases these photons, packets of energy. And so here we can actually see the emission for hydrogen. So it's not a continuous spectrum like this. It actually is just releasing very quantized, discrete amounts of energy, and these energies that we can see are right here. And what this does, it creates kind of like a barcode for each of the elements. We can identify elements based on their emission spectra. So this is going to be the barcode that tells us, oh, this element that is being energized here is going to be hydrogen. So you need to know that when electrons emit energy by jumping down these energy levels, they release photons, which are packets of energy. And the amount of energy, or the frequency, is based on the amount of energy that it took to jump these levels. And so different frequencies are the reason we get these different colors of lights, and the whole theory behind the flame test. A couple of things to note. You need to know this word convergence. Pretty much as these shell levels get higher and higher and higher, the distance between them gets smaller, and so they eventually will start to converge or get really, really close. The energy level differences between the larger shells here becomes less and less. Eventually, this electron can jump up these energy levels and eventually leave the atom, and the energy it takes to make it leave the atom, we call that ionization energy. So here are some of the different series that we can get from releasing energy. We're jumping from the second to the first, or the third to the first, and so on and so forth. This is the Lyman series. This is releasing ultraviolet light. We will not be able to see this. The Passion series is going to be releasing infrared light, so that's jumping from these levels. Now this is the Balmer series, which is what we see here with hydrogen. The Balmer series is going to release these lights. So here's that red, and the yellow and the green kind of make that aqua, and the blue kind of forms to make that purple line. And so these are because of the electrons jumping these energy levels and releasing energy of very specific frequency, and we can see that here. And this is all model for the Bohr evidence. Limitations of the Bohr model: the Bohr model is only good for one electron, so only for hydrogen. Past hydrogen, the data kind of falls apart. And again, here are just some values that represent kind of the diagram that we are looking at here. Okay, Heisenberg and the equation. So pretty much what Heisenberg said is that it is incorrect for us to kind of, write the electrons as little dots. Instead, we have to consider them as clouds of probability. So instead of writing a ring and saying the electron is probably somewhere in this ring, we cannot do that. What we can do, however, is say that the probability of an electron being in this cloud is very high. And the reason we cannot assign electrons these kind of like particle-like structures is because of his uncertainty principle. And the way to describe it is this. So let's say you have a dark room, and inside that room there was a tennis ball somewhere, and you wanted to figure out where that tennis ball was in that room. Now, the only way to find out where that tennis ball is, it's dark in there, is to throw a tennis ball and wait till you hit that other tennis ball. Now, the only problem is as soon as I figure out where this electron is by hitting it with this tennis ball, when I hit it with the tennis ball, the electron's going to move. And so Heisenberg's uncertainty principle says that you can never figure out the position or the velocity of an electron. And so this is something that we just have to assume about the universe, is that we cannot ever determine the position of the electron because of this uncertainty principle. Because every time we prod it or try to figure out some data on it, it moves because we are influencing it with whatever tool we're using. And so we have these orbitals that help us determine where the electron has a high probability of being. We have S, P, D, and F. So S is spherical shaped, P is kind of dumbbell shaped, and D and F are these weird shapes that we have here. Now, these electrons have orbitals, or these are orbitals that hold electrons. The S can hold one orbital, which is 2 electrons. Every orbital can hold 2 electrons. The P can hold 3, so 6 electrons, and D can hold 5, so 10 electrons, and F can hold 7, so 14 electrons. By the way, these letters, S, P, D, and F, they're not just random. They come from the descriptions of the atomic line spectra. Char principle, fuse fine, SPDF. Okay, so let's talk about some rules when trying to figure out where these electrons go into these orbitals. Let's start off with Pauli's exclusion principle. It says that no 2 electrons can have the same quantum number. What does quantum number mean? Pretty much they can't be at the same place at the same time with the same amount of energy. And Aufbau's principle says that the lowest energy levels are filled first. We're going to use this diagonal rule to figure that out. And then we'll talk about Hund's rule in a sec, okay? So, as you get more and more electrons, so hydrogen has 1 electron, helium has 2 electrons, lithium has 3, and so on and so forth, I have to fill them according to this chart because this is the lowest energy, as you can see here, and this is the highest energy. And if I were to follow this, it goes pretty much in order. It goes 1s, 2s, 2p, 3s, 3p. But then where it kind of gets weird is right here with the 4s and the 3d. So the way I can figure this out without having to memorize this is through the diagonal rule. So we see here 1s, 2s, 2p, 3s, 3p. And instead of going to 3d here, I just keep following the diagonal up to 4s. Then I go to 3d, 4p, 5s. And so I can figure out, I can make sure I'm following Aufbau's principle by using this diagonal rule. Now, if you remember, we said the s orbital can fit 2 electrons. The p orbital can fit 1, 2, 3, 4, 5, 6, and the d orbital can fit 10 because it's got 5 of these orbitals. Now, when I'm filling these orbitals, I have to follow Hund's rule. And the way I remember Hund's rule is, as a teacher, whenever you're going on a field trip, you always want to make sure your kids are safe on the bus. And the way to make sure that no one gets into a fight or no one starts making out or anything like that is you make sure all of the seats on the bus are filled up before you start doubling kids up. So you have 2 ways of putting electrons in here. Well, you have to fill up the s orbital first because of Aufbau's principle. I have to fill up these 2 seats. I have to fill up these 2 seats. Now I'm moving on to the 2p orbital. I can do this 2 different ways. I can put 1 kid in each seat like this, or I can double up a kid here, 1 seat, and leave this seat open. Now, this is a recipe for disaster. And so what you want to do is just remember, fill every seat first, no empty seat on the bus, and then only then can you start doubling up the other seats. Also notice electrons this is not violating Pauli's exclusion principle because these electrons are filling, yes, the same orbital, but have what's called different spins. So these have an up spin and a down spin. Also, when we're doing Hund's rule, make sure that all of these electrons are parallel in terms of their spin. Another way to do the electron configurations, instead of following the diagonal rule, is to take a look at the periodic table. And so this is the S block over here, the P block over here, and the D block and the F block. And so when you're doing electron configurations, let's say like carbon, which is 6, the way I would do the electron configuration for carbon as I just follow it from left to right and going down. So 1s1, 1s2, 2s2 right here, 2p2. So carbon's right here, 2p2, so I can figure that out. What else? What if I wanted, I think this is magnesium. Magnesium would be 1s2, 2s2, 2p6, 3s2. Notice it kind of gets a little bit weird with, there's these exceptions here that we will talk about with D4, D5, and D9, D10. And we're going to talk about it right now. So weird electron configuration. First, a little terminology. The valence electrons are the electrons in the outermost energy level. Okay? So for D block elements, you need to know certain things. So if we go back here, the 3D sublevel is actually lower in energy than the 4s orbital is actually lower in energy than the 3D orbital. That's why we fill it first here before moving on to the 3D. This is only for elements below 20. Once we start getting into this D block, this is 20 right here, this is calcium. Once we start getting into this D block, then as soon as we start filling in this D block, this actually becomes lower in energy than the 4s. And so let's take a look at that. So the 3D sublevel is written because the 3 sublevels falls below the 4s once the 4s is occupied. And this is elements after calcium. So once the 4s is occupied, it actually falls lower in energy than the 3D. Or the 3D actually follows lower in energy once the 4s orbitals are occupied. Also, there are two exceptions that the IB likes to ask. One is on chromium and one is on copper. So we see here that there's two places I could be putting this final electron right here. I could be filling this whole 3D orbital, or I can be putting this electron with the 4s over here with a downward spin. However, it turns out that this is more energetically stable, having a half-filled 3D orbital rather than a filled 4s orbital. Same thing with copper. It is more electronically advantageous to have a full 3D orbital than a half-filled 4s orbital, rather than having 9 in the 3D and having a filled 4s orbital. Noble gas notations. So when you're getting really higher into the atomic numbers, lower in the periodic tables, it can be tedious to be writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, d10, so on and so forth. So we have something called the noble gas notation, where this is neon and this is sodium. They share this section of the electron configuration. So I can just write it according to noble gas configuration, which says, hey, let me just copy down the part. Let me just represent the parts at the same by writing the noble gas and E in brackets, and then just writing what is different afterwards. So one last thing we got to talk about is the electron configuration of ions, anions, and cations. So anions is when we gain extra electrons. So here's sulfur 2-, so it has 2 extra electrons. And all we're going to do is treat it as if it has those 2 extra electrons. So regular sulfur ends with 3p4, so we're just going to add 2 electrons. It's going to now be 3p6. Now cations, which are positive, the rule you need to remember is that for the transition, or that D block, that darn D block, it's got a bunch of rules. When they form ions, they're going to lose electrons, but they're going to lose it from the 4s sublevel before the 3D sublevel. So here is chromium 3d5 4s1, and if we're going to lose 3 electrons, we're going to lose the 4s1 first before we start taking away from the 3d5. Again, this is because the 4s is higher in energy than the 3D once the 3D sublevel starts getting filled.